Hello everyone. In this video I'm going to be going over several examples in which we are given a set of functions and asked to determine whether that given set of functions is linearly independent or linearly dependent on some interval. Right? And hopefully the concept of linear independence and linear dependence of, say, vectors, that might have come up in a prior linear algebra course you've taken, hopefully. If not, I'm going to refresh your memory as to what it means for a set of vectors, or in this case a set of functions, to be linearly independent. Alright, so let's get into it. So for this example and all three, I'm going over three examples in this video. I have the same set of instructions, and they're this. So determine whether the given set of functions is linearly independent on the interval, from negative infinity to infinity, so on the entire real number line. Alright, so before we get into the example, let's talk about what it means for a set of functions to be independent. So a set of functions say f1, f2, all the way up to say fn are linearly independent on some interval I say on some interval I, if for every value in that interval, right, if for every input in the interval, for every x, say, belonging to I, the equation c1 times f1 of x plus c2 times f2 of x plus all the way to plus cn times fn of x equals 0 if this equation has only the trivial solution. Right? If the only way this equation is true is when all the constants c1 through cn are all 0. So if for every x in this interval this equation has only the trivial solution, c1 equals c2 equals equals cn. If they're all the only way this is true is if all the constants are 0. If we can find another set of constants that are not all 0 that make this true for some x in the interval, then that means we can write one of these functions as a linear combination of other functions, for that value of x in that interval, and they're not independent. They'd be linearly dependent in that case. So if there's more than just this trivial solution to this equation, then the functions are considered linearly dependent. Right. Okay, now sometimes these functions are all of different types, maybe some polynomials, some exponentials, logarithms, trigs, whatever. So what you'll see happen here is I'm trying to solve this equation for C1, C2, I'm trying to find constants that make this true, C1 through Cn. And what can happen here is you create a system. You create a system by differentiating with respect to the variable x. And that system will consist of, this equation that I started with, and then you have, c1 times f1 prime of x plus c2 times f2 prime plus Cn times Fn prime equals, 0. The derivative of 0 would be 0. And I would do this until we create an n equation, n unknown system, an n by n system. So you have the one equation there too. So to create this system, we go down all the way to the n minus first derivative of f1 and f2 and f3 and so on. Cn, then the n minus first derivative of fn equals 0. And then we have this system here, which then I can, write this write this as a matrix equation this way. And as a matrix equation, this looks like this. We'd have the matrix involving all the functions and their derivatives, so f1, f1 prime, all the way down to the n minus first derivative of f1. And the same would go for all the other functions, all the way up to fn, then fn prime, all the way down to fn, and then the n minus first derivative. You have this n by n matrix here, times these constants, c1, c2, down to cn, and this needs to be equal to, the 0 vector with n zeros. And this matrix here, right, this matrix made up of all their functions and their, their derivatives, if those derivatives exist. This matrix is called the Wronskian. Of those functions, of functions f1 through fn, and it's denoted this way as, w of f1, comma f2, comma f3, comma to fn. All right. So you just, those functions up top and all their derivatives below. And the only way this system's going to have the trivial solution, the only way that this equation, will have just c1, c2, cn equals 0 as a solution, is if this matrix is invertible. Right? And actually, the Wronskian is the determinant, I should say. I apologize. The Wronskian is the determinant of this matrix. So maybe I should write that. Wronskian is the determinant of this matrix of derivatives. So from all this discussion here, these functions f1 through fn then are independent on some interval. They're independent, linearly independent on I, when the Wronskian of this set of functions is non-zero for all the values in the interval. All right, and this is huge. Okay. Because in order for this equation to have only the trivial solution, where c1 through cn is 0, this matrix needs to have an inverse, and the only way it's going to have an inverse is if its derivative is if its determinant is non-zero. And this has got to be the case for every value in that interval. Okay, so this gives us a couple options, to try to determine whether a set of if a set of functions is independent or not. We could start off with this equation and see if we can, spot a non-trivial solution. And if we can spot a non-trivial solution to this equation, then they're definitely dependent. But if we can't spot one, perhaps we should go to the Wronskian and go from there. All right, so I'll actually do both for each of these examples. Okay. So back to my after all that, back to my question. These three functions, f1, f2, and f3, I'm asked, are these functions linearly independent or dependent on the real number line, right? For any x. So one way I'll do it is to look at that equation. Right, let's look at the equation. C1 times f1, so c1 times x, plus c2 times f2, c2 times x squared, plus c3 times f3, which is the c3 times the quantity 4x minus 3x squared, and ask when is that equal to 0? For what values of c1 and c2 and c3 could I get this left side to be equal to 0? I'm hoping it's pretty obvious here. There's probably actually quite a few solutions you could probably think of. But if I simply let c1 equal to 4, right, because you got 4x there, c2 be equal to negative 3, and then c3 be negative 1, you'll have a solution. So look, you got 4 times function 1 plus negative 3 times function 2, and then plus negative 1 times function 3, you'll see is indeed equal to 0. Right? Is you have 4x minus 4x, negative 3x squared plus 3x squared. So this here, definitely a non-trivial solution. And this is for any x. Right? This is a non-trivial solution to this equation. And this would be the case for any value on the real number line, right? For any value in that interval. So because we could find a non-trivial solution for just some value in this interval, then definitely these functions are linearly independent. So the function f1, f2, and f3 here are linearly dependent, right? They're not independent because I could find non-trivial solutions to this. So they're linearly dependent. And if that's the case, that means you can write one function as a linear combination of others in the set. And again, hopefully it's obvious that you could write f3 as just 4 times f1 minus 3 times f2. Right? Because it's just 4 times x plus negative 3 times x squared. So if you can write one function as a linear combination of some other ones in the set, then clearly that set of functions is not independent, because one can depend on the others. And this would be for any x in the interval. Now, the other way you could do this too is by looking at the Wronskian. Of these three functions. Right? So that's w of x squared, and then 4x minus 3x squared. So remember I said that this is the determinant of the three functions here. So this will be a 3 by 3 matrix where I have the functions up top, x squared, 4x minus 3x squared, and then their derivatives up to the second derivative. Right? Three functions, we go up to the second derivative to create a 3 by 3 matrix. So derivatives with respect to x would be 1, then 0, right? Derivatives of this function would be 2x, then 2. Derivatives of this function would be 4 minus 6x, and then negative 6. Okay. And then really, based on my previous line, you could take the determinant with x's the way it looks right now, or you could plug in a value from any number on the, plug in any value from this interval that all these functions are defined on and see if the determinant is 0 or not. Now, I told you earlier, this f3 is equal to 4f1 minus 3f2 no matter what x is. So based on my previous work, I can tell you that no matter what I replace x with, no matter what value on the interval I look at, this determinant will be 0. All right. Now, say you didn't realize that. Say I didn't do all this previous work. Let me just do I'll just do cofactor expansion down the first column. So remember how determinants go. This would be x times the minor 2x, 4 minus 6x, 2 and negative 6, and then minus 1, right, because it's in odd position, times its minor. And hopefully you remember how to take determinants from a linear algebra class. And if you don't, look up determinants of a matrix somewhere on YouTube or something. All right, and then plus 0. And I have here x times, negative 12x. Then, it'd be minus 2 times 4 minus 6x here. So minus 8 plus 12x. We'll simplify that in a second. And then minus 1 times, we have negative 6x squared. And then minus 2 times this would be minus 8x. And then plus 6x squared. And hopefully you can see that no matter what I replaced x with, right? And again, you could have replaced x with some specific value if you wanted to show that they were dependent, because this determinant needs to be 0 for only one value in the interval. This determinant needs to be 0 for only one value in the interval to show that the functions are linearly dependent on the interval. Right? To be linearly independent, this determinant needs to be non-zero for every value in the interval. So a lot more to show. But this is 0. Because you see here I'd have negative 8x plus 8x. So this is 0, and then this is, for any x in this interval. All right, so x equals 1, x equals 2, x equals pi, whatever. So based on that, we can then say again that these functions are linearly dependent on the real number line. Okay. So let's get into my next example. All right, the next example, 3 different functions. Not every example you come across is going to have a set of 3 functions. You might have a set of 2, set of 4, whatever. All right, so same deal. We're asked to determine whether the given set of functions is linearly independent on the entire real number line. So the first way to do this is to, again, look at the equation. C1 times 5, C1 times F1, plus C2, some constant C2, times, F2, which is cosine squared x, plus, and then C3 times F3, sine squared x. When's this equal to 0? And does this have, are there any values of x on the real number line for which this equation will have a non-trivial solution, where C1, C2, and C3 are not all 0? Now, if you can't find that, right, if the only solution to this, the only way this is going to be true is if C1, C2, and C3 are all 0, then they're linearly independent. But if you can find, just at least one value in the real number line, one value of x where this is true when C1, C2, and C3 are not all 0, there's a non-trivial solution, then you can say the functions are linearly dependent. All right, well, this one here, again, just from inspection, looking at this, just recall that for any x, You might have to use some identities or some formulas that you've seen in previous courses. Recall that for any real number x, for any x, cosine squared x plus sine squared x is always equal to 1. So I'm going to use that fact to help me out here. I can very clearly see that these are going to be dependent. I can find a non-trivial solution to this. All right, let's suppose I just let let C1 very easily just be how about -1/5, and then let C2 equal 1 and C3 equal 1. And then we'd have 5 times -1/5 plus, cosine squared x plus sine squared x equals 0. And this is indeed true because it is it's the typical Pythagorean identity that we know. Because I'd have -1 here, I would add it to both sides and get cosine squared plus sine squared equals 1. So again, I have found a non-trivial solution to this equation. And again, this works out for any x in the interval on the entire real number line. All right, so based on that, because I was able to find a non-trivial solution for for some x, in fact any x on the real number line, again these functions are linearly dependent, not independent. Right? They're linearly dependent, just like in my first example. Right, and in fact, you could express one as a linear combination of the others, right? Since they're dependent, let me show you. I could say that f1 is simply 5 times f2 plus 5 times f3. Right? There's a relationship showing that one function is dependent upon the others. And this is good for any value of x in that interval for this example. All right. Now again, the alternate method to showing that these are linearly dependent would be to use the Wronskian. So what's w of 5 cosine squared x sine squared x? So remember again, this is the determinant, and it's 3 functions, so it should be a 3 by 3 where the first row are my functions, the second row is the first derivatives, and really you could call this this is the same thing here as negative sine of 2x, right? 2 cosine x sine x, and this would be 2 sine x cosine x, which is again just the same thing as the sine of 2x. And then final row is the second derivatives. So 0 again, then -2 cosine 2x, and then +2 cosine 2x. All right, and then hopefully you can see that this determinant will be 0 no matter what x is. Now, if you wanted, based on previous work, they're dependent. So again, if you can find a value of x in the interval, just plug in, say, pi or something. if you can find a value of x, replace all the x's with that value, and if the determinant is 0, then you have found a value for which the functions are clearly dependent. But I'll show you that this is 0 for any x, right? Just kind of going through this. I'll just do cofactor expansion down the first column again. So 5 times its minor. And hopefully you see that when I do the determinant of this 2 by 2 matrix, it is 0. Because you'd have negative 2, sine 2x, cosine 2x. Then plus 2 sine 2x, cosine 2x, so they'd cancel it. This is 0, and this was for any x in that interval. But you don't have to show it's 0. If it's 0 for at least one value in the interval, if this determinant is 0 for one value in the interval, then the functions are dependent on the interval. All right, so therefore, again, the set of functions is dependent, linearly dependent on this interval. As I said in the previous page. Right. Okay, so again, 2 different ways to show dependence there. All right, now I know you're thinking, hey, are we ever going to get to an example where the functions are linearly independent, where this determinant's non-zero for all the values in the interval, for every real number. So that's what I've got in my last example. All right, so I've already spoiled it. All the functions, the set of functions in my last example here are linearly independent. Okay, but let's show this. All right. So the functions now are f1 is 1 plus x, f2 is just x, f3 is x squared. All right. So again, the first method to see if you're independent or dependent is to look at that equation. Right? Look at the equation, c1 times f1 plus c2 times f2 plus c3 times f3, and say, hey, when's that equal to 0? Right. Now, being all polynomials here, this one's actually easy to set up a little system for, right? This would be equal to c1 plus, and then putting the x terms together, you'd have c1x plus c2x, so that's c1 plus c2 times x, and then there's only the 1x squared term, right, plus the c3x squared. And being polynomials, right, we can set up a nice easy system. Remember, the only way polynomials are equivalent for all x, on their domains, the only way polynomials are equivalent is if their coefficients are the same. So equating coefficients of polynomials here, and again, the only reason I'm doing this is because these are polynomials. So equating coefficients of the polynomials, I have the following system. We have c1, then the constant terms must be the same, so c1 must be 0. The linear coefficients must be the same, so c1 plus c2 must be equal to 0 as well. And the quadratic coefficients must be the same. c3 must be equal to 0. Well, that implies that c1 must be 0, and if c1 is 0, then this second equation implies that c2 must be 0, and the third equation implies that c3 must be 0. And this was true for any x, right? Again, the only way polynomials are equal for any x is if their coefficients are the same, coefficients of like terms. So the only solution to this equation for any x is the trivial solution, where all the constants need to be 0. And if that's the only solution to this equation for any x, for any value in the interval, that means that these functions are linearly independent on this interval. So f1, f2, and f3 here are linearly independent. on the real number line. All right, independent. Sorry, my spelling. I have to scratch that and respell it. Independent. Sorry about that. But they are linearly independent on the real number line. All right, wonderful. And that means that there's no way I can write one of these functions as a linear combination of some others. So I can't, like I did with the previous examples, where I like the first example, f3 was 4f1 minus 3f2, right? I can't do that here. You can't write f3 as some linear combination of f1 and f2. You can't write f1 as a linear combination or a multiple of f2 and f3. It can't be done. They're independent of one another on the real number line. All right, so again, one approach to that. Now, this isn't always able to be set up. So very often, I would say just look at the Wronskian. So again, here I have the Wronskian. So w of 1 plus x, x, and x squared is the determinant of yet again another 3 by 3. Again, they're not always 3 by 3. You might come across other problems again with more functions or less functions. So first row, 1 plus x, x, x squared. Next row is the derivatives, 1, 1, and 2x. And then second derivatives, 0, 0, and 2. And then I'm just going to do now again, you can replace x with, now here's the problem here. Since I already know that these are independent functions, replacing x with a single value, you're going to get a non-zero determinant. Well, that just tells me that that it works for that one value. To show that functions are independent on an interval, this determinant has to be non-zero for every single value in the interval. So this is a case where I know that plugging in a value isn't going to help me. Now, if they're dependent, if you find one value that makes this determinant 0, you can plug it in and show that, and then you'll show that the functions are dependent on the interval. But independent's a little trickier because you got to show that it's non-zero for every value of x, and that would be impossible to do because there's no way you can plug in infinitely many values. So I'm just going to keep these the way they are again. And I'm going to do cofactor expansion down the third row because there's a bunch of zeros here. So this is going to be equal, so this is 2 times the minor for this third row, third column position, which would be 1 plus x, x, 1, 1. Right. And hopefully you can see that this is, 2, and then you have 1 plus x minus x. So that's just 2 times 1, which is 2. So no matter what you plug in for x, the determinant of this matrix is 2, right? This is not 0, and this is again for any x, right? Because I left x the way it was. This would work out as the determinant of this matrix is non-zero for any x, implying that the functions are independent of one another, right? Functions are linearly independent on this interval. Right, and you can't write one of them as a multiple of others or as a linear combination of others. You can't do that. All right, so again, multiple ways to go about it. I would recommend just jumping to the Wronskian. It's very quick. It's pretty quick and easy, especially if there's only a few functions like these examples here. But again, if you see something, like a trig identity, like I saw the sine squared plus cosine squared equals 1 thing from the second example, if you see something that clearly shows the functions are dependent, just write that. There's no need to go to the Wronskian. But it never hurts. It can't hurt to just jump to the Wronskian and show, hey, there's going to be a time where this determinant's 0, so they're dependent. Or show, hey, there's never a time where the determinant's 0, so they're independent. Okay, simple as that. All right, so hopefully watching these 3 examples helps you out when you're working on questions similar to this, and thank you very much for watching.